Hey, whoops. I like to start off with black just to be able to write it out. What is the Lewis structure of C2H2? Now, I have noticed that I do take a little bit of an unorthodox method when I do Lewis structure, but I'm going to make sure I explain my steps thoroughly and refer to how the other person did as well, just so that we fully understand what's going on. So what I like to do in Lewis structures, because I kind of memorize this, is that carbon usually likes to be in the middle, depending on what it's paired with. So like things that are centralizing are things like carbon, nitrogen. There are a few other examples, but what I would like to focus on is more so that if you're dealing with halogens, so if you go to the periodic table and you see the like fluorine, chlorine, bromine, those ones usually like to be at the ends, okay? And we flip that over, same thing with the alkali metals and hydrogen. They like to be at the end. You rarely see them in the middle. And things like oxygen as well, like that row, they also like to be at the ends. Like if you had CO2, carbon dioxide, for example, you'd have carbon in the middle, and that would be CO2. But I didn't really explain how I got here, so we're going to ignore this one, shift it all the way in this corner, and actually focus on what we want, C2H2. So the way I do this, as I mentioned, is that because I'm quite familiar with it, I like to start with what's in the middle. So I have two C's. But before that, I also like to note how many electrons, specifically on the outer shell, does each contribute. So if you refer to the periodic table, right, hydrogen, oops, I don't even know what I did there. Hydrogen is right there, number one. So each hydrogen has just one electron. So one electron, and there's two of them, so that's two electrons it can offer. Carbon is right here, row 14, and because it has that two shells that are filled like it's the lowest shell, the next shell has 4 electrons in it. That's how we got that. And the reason being is because if you notice, it goes 1 is 1 electron, 2 is 2 electrons, then we skip all the way to 13 because everything in between are transition metals, and 13 is 3, 14 is 4, nitrogen is 5, oxygen is 6, 16 is 6, 17 is 7, and 18 is full. The reason why is because if you notice, some of them obviously are in rows further and further down, but this is just a good way to know what's in the valence shell, like the most outer shell. So with that being said, carbon 4 on its most outer shell, 2 of them, so that's 8. So in total of outer electrons I have to deal with is 10. Okay, so with that, let's see what we can do with this. So 2 carbons in the middle, just gonna put hydrogen on each side. I just assume that they're balanced like that, and now we need 10. So let's see, we need to make bonds between each one, so that's 1, 2, 3, 4, okay, 5, 6. Now with this being done right now, we've only accounted for 6 out of the 10. Now the thing with carbon is that it still wants to be as full as possible, you know, so we have to figure out a way to kind of balance it out. So just in a sense throw the electrons anywhere we want, but let's try to make it even. So 6, 7, 8, 9, 10. So with that, right now this looks like this. And this isn't right. So carbon likes to have 8 in a sense of its valence shell, whether shared or unshared. But if you notice, right now it has, because it's sharing with hydrogen, right, it has only 2, 4, 5, 6. Same with this carbon, 5, 6. So how do we get it to where there's more? What we actually can do is move each of these electrons over to form a bond. And when we do that, when we put both of them there, you actually end up with this, right? And now because it's sharing those bonds, you have now 2, 4, 6, 8. So now this carbon is full, and same with the carbon on the other side. They're both full actually. And as a last test, to make sure you have the right number on it in terms of the electron number, you can actually do the math to see what it's supposed to have. So 4, okay, minus the electrons that are unpaired, so it's 0 for carbon, plus the electrons that are paired, so that's 8 divided by 2, and see what we get. As long as we get 0, that means we're good. And hydrogen, we can actually do the same test. 1 minus 0 plus 2 over 2 also equals 0. So these two both check out. So this indeed is the most stable form. Now let's make sure we get into our Lewis structure. So what we have is C. I like to just draw my electrons like that. Specifically, they ask for Lewis structure because they want you to be able to see your electrons. And that right here is the Lewis structure for C2H2. Let's see what they did. So they find a degree of unsaturation through that equation, which honestly I'm not too familiar with. What it looks like they do is that they 2 plus 2C. Oh, interesting. So it's kind of like trying to find what type of bond it is, and it does based on the degree of saturation of unsaturation, the p-value. They can assign which bonds they have. Based on this, what they got was that it has some 2 pi bonds, and those bonds are actually what's used when forming double or triple bonds. So with that, they were able to, I guess, systematically show that there was actually a triple bond between the 2 carbons based on the math they did. I kind of did it in a more simplistic way where I kind of just go through trial by error, and that's really what it is. So just as a review, make sure you know exactly how many electrons they actually contribute, because that's the easy way to keep track. And you always want to check once you're done and you got your picture that it does actually add up to what it says it should. We do have 10 here, so that's good. And then the last check for me is to try to find the number, the electron number. I believe that's what it's called. But yeah, where you try to figure out what it usually has, which is 4 and 1 for carbon and hydrogen respectively, and what it's actually given. So in this case here, carbon is sharing all of them, which is why there's 8/2. In this picture right here, for example, let's say we use this and try to do our math, you'd notice it'd be 4 minus 2, because there's 2 here, and then it's sharing, plus 4/2 equals 0. So it would still check out. The only issue is that in this case here, carbon has only 6 out of 8 possible electrons, so it's still missing 2, which is quite unstable. So that's why this one wouldn't work, and hence we got the triple bond. Okay, so with that, hopefully that explains how we did it. While I write this correct, you are free to pause the video, take a snap of this, just so you can work through it yourself. And yeah, so let's move on to question 4.